So the NU32 is what we call a breakout board for the PIC32 MX795F512H. This is a surface mount chip. It doesn't come breadboardable, so it can't just plug into a breadboard. And it's pretty difficult to solder because it's so small and it has 64 pins. So we have a manufacturer produce a breakout board that we've designed that breaks out all the pins and applies power to the correct pins and has an oscillator and does all the things that make this chip work without using too much pins, leaving most of them available for you to use for projects. Let me draw like a flow chart or block diagram for exactly what the NU32 does to integrate with the PIC32. The first thing we'll concern ourselves with is power. So we'll have a V-in pin, which is also connected to a DC jack. And that's going to go to a chip called a 5-volt regulator to generate 5 volts. Okay, we generate 5 volts because 5 volts is still very useful in lots of types of components that we'll want to talk to, like LCDs. But the PIC itself is going to run at 3.3 volts. So we'll take our 5 volt and go into a 3.3 volt regulator. Okay, now 3.3 volt regulator outputs 3.3 volts. Where does that go? That will go to the PIC32. And there are a bunch of pins. All the VDD pins get connected to 3.3 volts, and all the VSS pins go to ground, and then there's a variety of capacitors on all of the regulators and the PIC32 to make sure that all of these voltages don't have too much ripple to reset the PIC and do bad things like that. We're going to take that 3.3 volts and we're going to attach it to a red LED. Okay, so here's our LED and it's red. That's our power indication LED. So when you turn on the power to the board, that red LED should turn on. Now, why wouldn't that LED turn on? Maybe you've hooked up something like 5 volts to ground or 3.3 volts to ground and there's a dead short. Or maybe you're just drawing too much power from one of these voltages and the red light is flickering or something. So those are your indications for something wrong is happening. What do we mean to have a voltage regulator turning some voltage input to 5 volts and 3.3 volts? So these are what are called LDOs, low dropout voltage regulators, meaning that they don't need a whole lot of voltage on the input to make voltage on the output. So the voltage regulator on the input of the NU32 needs something like more than 6 volts to be able to make a consistent 5 volts. It's actually a little bit better than that. You could probably get away with 5.2 volts. It just depends on how much current you need on the output. But if you put more than 6 volts onto the input of this regulator, it will be able to make 5 volts at 1 amp. So you could draw as much as 1 amp as you want from 5 volts. And then the 3.3 volt regulator is able to produce up to 800 milliamps. So if I wanted to put a resistor from 5 volts to ground, what would be the largest resistor I could do? Well, I could just calculate V equals IR and set I to be 1 amp and see what resistor that would be, and I could put that resistor here and everything should just barely still work because I'd be sucking up pretty much all of the current, and we want to reserve a little bit for the PIC. How does a regulator turn 6 volts into 5 volts? Well, it really just burns everything off as heat. So that extra volt that we supplied is being burned off as heat, and that's what really limits these currents. The more current we draw here, the power that's dissipated by this chip is the difference in the voltages times the current. So if I have 6 volts here and I'm outputting 5 volts, I have a 1 volt drop times the amount of current I draw at 1 amp. That would be 1 watt of heat needs to be dissipated from a pretty small surface area of this little chip. So at some point it just can't dissipate the heat fast enough, and then it gets too hot, and then it has to turn itself off, and that's when bad things happen. So that's where the 1 amp limitation comes from, and the 800 milliamps. But really, we don't want to get anywhere near that amount, because as we approach that amount, it gets hotter and hotter. So really, a safe amount here is maybe half an amp and maybe 200 milliamps. Once you draw that much, we start to get very hot. Another limitation might be you could supply this chip with 12 volts, and the regulator would take 12 volts and still make 5. Now we're dropping 7 volts across the regulator. And that same amount of current that we're drawing times 7 volts is a lot more heat. So generally, we don't want to apply too much voltage here so that we don't generate too much heat. And the regulator has a specific maximum voltage on its input as well. I think it's something like 16 volts. So we don't want to apply more than 16 because that's just some other absolute maximum. So that's our power system. There's actually one more regulator. The PIC32 core runs at 1.8 volts. But we never see that anywhere. That's all internal to the PIC. So we don't have to really worry about 1.8. But it does exist somewhere. Okay, the 3.3 volts also goes to power another chip on the board, the Ftdi chip. The Ftdi is a USB chip. So this goes to the USB connector. The USB cable also provides 5 volts. We're only using it though to power. We're not using it really to power anything because we don't want to accidentally touch a voltage that when we start building motor projects to this USB cable and then fry your computer. So this isn't isolated in that that chip still does have pin, and if you dragged a wire across your board, you could short things. So try not to do that. But we're semi-protected. And between the PIC and the Ftdi chip are 4 pins called UART pins, or serial pins, and the Ftdi chip is a serial to USB converter. So when we want to send data or a new program to the PIC32, it's coming from the USB cable to the Ftdi chip and then into the PIC32. Then we have 3 more items on the board, and so they're all coming from the PIC. So I'm going to draw them over here. There's 3 more pins, but it gets complicated. So these 3 pins are going to come back over here. And we have a button on the chip, and the button is wired like this. It's 3.3 volts to a pull-up resistor, and here's our button to ground. And the voltage between the button and this is a 10K resistor goes to the user pin on the PIC32. Actually, this might be 2.2K. We should go and look at the exact drawing. I can't remember if it's 10K or 2.2K. Either way, though, when the button is not being pushed, this is a high voltage because of the pull-up resistor. And when the button is pushed, we get low voltage. And there's no short when you push the button because the current goes from 3.3 to ground. The specific pin that the user button is attached to is pin D7 on the PIC. And this has no other functionality than we've just pre-wired one button for you to be able to use. We've also pre-wired 2 LEDs. So these LEDs go from 3.3 volts to the LED to a resistor into a pin. And so we call one the LED 1 pin, and then we've got another one, LED 2. And these are pins F0 and F1. And notice, and these are green, and I think they have a 330 ohm resistor in series with them to limit the current. So when this pin is high, the LED is off because if both sides of the LED are high, then no current will flow. When this pin is low, current will flow into the chip, and light will come out of the LED. So all of these things you could kind of think of as being wired backwards. The button, when you push it, outputs a low, and when the pin outputs a low, the LED turns on. There's a lot of historical reasons for why we do things like this, but we can easily check if the button is broken by when we first turn on, we assume nobody's reading the button. We read the voltage, it's high. That would tell us the button's not shorting or something. And then our chip typically is capable of inputting more current than it can output. We could check the data sheet. I think that might be true. In this case, we can input 10 milliamps, but we can only output 5 milliamps, something like that. So traditionally, these kinds of things are wired into the chip so that you can get more current and get a brighter LED. But remember, in code, when you say, I would like to turn on this LED, that means you need to turn the pin off. Sounds a little backwards.